This is the third in a series of resources that consider the four different types of sequences. Part 1 defines sequences and also considers sequences defined by a general rule. Part 2 inspects arithmetic sequences, the general idea, how to find specific terms in the sequence, and how to find a partial sum of the sequence. Part 3 looks at geometric sequences, the general idea, how to find specific terms in the sequence, how to find a partial sum of the sequence, and also how to find the finite sum of infinite series. Part 4 considers recursive sequences. We look at the basic rules and formulas, then work through examples of each. The basic idea of a geometric sequence is very similar to that for an arithmetic sequence. In geometric sequences, we obtain the next term by multiplying by a constant, non-zero amount. This amount by which we multiply is called the common ratio. To find the common ratio, divide the second term of the sequence by the first. The formal definition for a geometric sequence is that a sub n equals a sub n minus 1 multiplied by the common ratio r. Suppose we want to find the first four terms of the geometric sequence that has a first term of 7 and a common ratio of -2. Since we are given a starting amount for the geometric sequence, a sub 1 equals the given 7. To find a sub 2, we need to multiply the previous term by the common ratio. We have 7 multiplied by -2. Therefore, a sub 2 equals -14. A sub 3 will then be the -14 multiplied by -2, which equals 28. Multiplying 28 by -2, we find a sub 4 equals -56. But what if we want to find any term in the sequence? We could just keep multiplying, but there is a nice general formula to find the nth term of a geometric sequence. A sub n equals the first term, a sub 1, multiplied by the common ratio r, raised to the power given by the quantity n minus 1. The n minus 1 is needed since the repeated multiplication does not begin until the second term of the sequence. For example, we want to find the 11th term of the geometric sequence that starts with 5 and has a common ratio of 2. We begin with the formula to find a general term of a geometric sequence. A sub n equals a sub 1 multiplied by r raised to the quantity n minus 1. We want to find the 11th term. So we have a sub 11 equal to 5 multiplied by 2 raised to the quantity 11 minus 1. Subtracting, we have 5 multiplied by 2 raised to the 10th power. This leaves us 5 multiplied by 1024. And we find that the 11th term of this sequence equals 5120. Many of the tasks we want to complete with geometric sequences mirror those for arithmetic sequences. We may want to find a partial sum of the terms of a geometric sequence. To find the sum of the first n terms, s sub n, multiply the first term, a sub 1, by the quantity 1 minus the common ratio r raised to the nth power, then divide by the quantity 1 minus r. One thing to note is that there is no n minus 1 in this formula. We use the full n. Suppose we want to find the sum of the first 12 terms of the sequence 2, 6, 18, 54, etc. We need to find all the pertinent information so that we can use the partial sum formula. We need the first term, the common ratio, and the number of terms we will be adding up. The first term is given to be 2. The common ratio is found by dividing the second term by the first. We have 6 divided by 2, so the common ratio r is 3. And we are looking to sum the first 12 terms, so n is 12. Now we can plug into the formula and solve. We have s sub 12 equal to 2 multiplied by the quantity 1 minus 3 raised to the 12th power divided by the quantity 1 minus 3. Using a scientific or graphing calculator and copious use of parentheses, we can perform all these calculations at once. Doing so, we find the sum of the first 12 terms of this geometric sequence is 531,440. These sum problems can also lead to certain types of word problems. In the 1991 episode of The Simpsons, Bart gets hit by a car. Montgomery Burns hit Bart Simpson when Bart skateboarded into the path of the vehicle. Hilarity ensues. Suppose in an alternate version of the show, Mr. Burns offered the family a choice so as to avoid court and possible jail time. Either the family could accept $1 million or have a penny doubled every day for a 1-month, 30-day period. Which offer should the Simpsons accept? We need to consider this problem carefully. Because the penny is doubled daily, it is being multiplied by 2 each day. This makes it a geometric sequence. The first term is the value on the first day, 1 cent. The common ratio is 2. We want to find the total amount for a period of 30 days, which is our value for n. Now we can plug into the partial sum formula. We have 0.01 multiplied by the quantity 1 minus 2 raised to the 30th power divided by the quantity 1 minus 2. Using available technology, this results in a sum of $10,737,418.23. So this is clearly the better option. Unlike arithmetic sequences, it is sometimes possible to find the sum of the entirety of an infinite geometric sequence. Suppose we have initial term a sub 1 and common ratio r. If the absolute value of the common ratio r is less than 1, then the sum, capital S, of the entire series equals the first term, a sub 1, divided by the quantity 1 minus r. If the absolute value of the common ratio is greater than or equal to 1, then the series diverges, keeps getting bigger and bigger, and there is no finite sum for the series. For example, suppose we want to find the sum of the infinite series 4, -2, 1, -1/2, 1/4, etc. For this series, the first term is 4. The common ratio, dividing -2 by 4, equals -1/2. Since the absolute value of the common difference is less than 1, we can use the formula for the sum of an infinite series. Plugging in, we have the sum equal to 4 divided by the quantity 1 minus negative 1/2. Completing the calculations and simplifying, the sum of the series is 8/3.